Hello and welcome back to Advent of Code 2019. To day 21. Hello, Slinky. There is indeed an intro. Well, there's always been an intro, as long as I can remember. So, we're getting into the potentially harder problems. Not necessarily, though. Sometimes the difficulty stays around the same as we approach Christmas. In fact, the Christmas Day one is usually on the medium easy side because, if it was hard, then people would just spend the entire Christmas Day doing it and never spend any time with their families. That's programmers in a nutshell. All right, day 21. Spring Droid Adventure. Oh, so this is another int code problem. It's odd numbered. Looks like something to do with logic. Some sort of Turing machine-like thing. Alright. Is the music playing? Yeah. Alright. You lift off from Pluto. Oh yeah, because we've just... So this one was Pluto. And start flying in the direction of Santa. Where is Santa? While experimenting further with the tractor beam, you accidentally pull an asteroid directly into your ship. It deals significant damage to your hull and causes your ship to begin tumbling violently. You can send a droid out to investigate, but the tumbling is causing enough artificial gravity that one wrong step could send the droid through a hole in the hull and flying out into space. The clear choice for this mission is a droid that can jump over the holes in the hull, a spring droid. Okay. You can use an int code problem, blah, blah, blah. They run a simplified assembly language called Spring Script. It can remember at most 15 Spring Script instructions. Hello, DIJ. Yeah, it seems like we have a... It's int code, but it's also... They're talking about a modified, simpler... I don't know if it's simpler, actually. A different language, Spring Script. It looks like it's more restrictive. So can remember at most 15 instructions. The Spring Droid will move automatically forward automatically, constantly thinking about whether to jump. Spring Script programs only use Boolean values, not numbers or strings. Two registers are available, T and J. If J is true, at the end of the program, the droid will jump. They both start false, okay. Spring droids have a sensor that can detect whether there is ground at various distances in the direction it is facing. These values are provided in read-only registers. Your droid can detect ground at 4 distances. 1 tile away, 2 tiles, 3 tiles, and 4 tiles. Okay. If there is ground at the given distance, the register will be true. If there is a hole, the register will be false. Alright, fine. So you can see the 4 spaces in front of you. There are only 3 instructions available in Spring Script. And... set Y to true if X and Y are true. So the result goes to Y. So you AND X with Y and put the result in Y. Okay, and then you've got OR and NOT. In all 3 instructions, the second argument needs to be a writable register, either T or J. The first argument can be any register, A, B, C, or D. Okay. For example, the one instruction program not AJ means if the tile immediately in front of me is not ground, jump. Here's a program that jumps if a 3-tile wide hole is detected. So you jump. Trying to understand this. So there's a hole, so we jump. Oh, because at the end of this program, it's gonna decide what to do. Okay, so B will also be false, so we put true into the T. And okay, so we carry on jumping, not C, T, and TJ, and DJ. Why is this one different? Here we're setting I see. We only want J to end up true if A, B, C are holes and D is ground. That's what this script is doing. So only at the end of this will it decide whether to jump. And it will only jump if there's 3 spaces in front of it and a ground in the 4th space. Fine. Why specifically do we want that behavior? Okay, let's read on. The intercode program expects ASCII inputs and outputs. It will begin by displaying a prompt, then input the desired instructions 1 per line. End each line with a new line. Code 10, okay. When you have finished entering your program, provide the command walk, followed by a new line to instruct the spring droid to begin surveying the hull. I'm going to have to add a new method to my int code, which is input an instruction. Input a string, I mean. And it will have to convert everything to all the characters to ASCII, because otherwise I just have to keep doing that on the fly. If the spring droid falls into space... When you've finished entering your program, provide the command walk. Walk just basically means run the program. So if it falls into space... So we say not DJ walk. This sets J to true if and only if there is no ground 4 tiles away. In other words, it attempts to jump into any hole it finds. Oh, hang on. There's one point I've been missing. I guess that's how big is a jump? Well, let's look at this diagram. But it doesn't actually tell us, but it looks like it's 3 spaces, so it's like So if there's no ground 4 spaces away, 1, 2, 3, 4. Wait, what? Four tiles away. 1, 2, 3, 4. That's 5 tiles away. So this is A, this is B, C, D. No, that's correct. Okay, so when it gets here, then it sees the hole 4 spaces away, and it starts to jump. So it goes 1, 2, 3, 4. So it looks like you land 4 spaces away when you jump. If the spring droid successfully makes it across, it will use an output instruction to indicate the amount of damage to the hull as a single giant integer outside the normal ASCII range. Program the spring droid with logic that allows it to survey the hull without falling into space. What amount of hull damage does it report? So we've got to get... So we're trying to... Oh man. This is interesting. So we're trying to figure out a path to the end where our move is every step is either jump or don't jump. If we jump, then we stay in the air for 4 spaces. So if there's a hole in front of you, you would of course jump. If there wasn't, it's not clear whether you would jump or not, because there may be a unique sequence of jumps and weights needed to get to the end. So it's really a case of So every time we fall in a hole, we get... Do we really need... If the terrain has a fixed layout, we don't actually need this. Like, we should just be saying... Oh, wait. What the heck? This is a hard problem, I think. I'm not sure. Okay, so this script we give it, basically, all it can do is map a given configuration of A, B, C, and D to a true or false value for jump. So there's 16 possible combinations. One of those must be the correct one. That will just get us to the end, because otherwise it's impossible. We only give it this script and let it run. So do we not just try each of the 16 variations until we get it? we don't even need to look at this map or anything. Like, we either fail or we succeed. If we succeed, we get the answer. If we fail, we know we didn't pick the right one of the 16 truth tables. So that's it, right? That's the algorithm. It's a manual process. You could automate it, but how do you? Oh yeah, you would have to choose. All right, I think I know how to do this, but can only remember most 15 instructions. Yeah, that's how many you would need to define one of the truth tables. Well, you don't need as many as 15, but... So T and J both... Okay, I sort of get it. Excuse me. Alright, if my idea works, it's probably... That's all we need to do. I'm just worried about part 2. This could be a very hard part 2. Alright, so let's try this. Alright, I think we need a new method for encode as well. So let's copy some of this stuff. So we got that. Oh, we got our input. Okay. So now we already know that if A is a hole, we must jump. Like, there is absolutely no doubt about that. Everything else we don't know. Actually, no. If D is a hole, we mustn't jump. And if A is a hole, we must jump. Those are two bona fide rules. The only question is, so it's actually only 4 possibilities, not 16. What do we do with B and what do we do with C? So that's even easier. So let's add an instruction here as well. So we've got run encode. So we want a new method here. Let's say define put string s So in this, I would say we just put... We really basically did this before, didn't we? We said, how many times did we use this method here? Oh, no, this is not the one where we were putting strings. When did we do that? Probably 17. Yeah, this is what we did. Ord, car. Yeah. Okay, so basically, we're doing this. For car in S, self dot. And then we put in a ends line. So that puts a string in and puts the end line afterwards. Okay. So with that method, then you can say define for given B and a given C, define hang on, let's do it like this. So we say define create script for given A, B, C, D. So what this does is it creates a list of strings, i.e. the script that we would need if we want it to jump whenever, hang on, hang on, this isn't quite right though. We may want it to jump. Oh, no. I've got this slightly wrong. There's not a unique configuration where we want it to jump. There's actually a set of configurations where we want it to jump. We need to identify that set. So we do this. So we know A and D are fixed. We don't have to worry about A and D. It's literally just B and D. There's 4 possibilities for B and C. So what we're saying is some set of those we want to jump, and some other set of those we don't. So it's sort of like, how... Oh, I need to think about this. Oh, this is like it's like De Morgan's laws or something. I'm not sure how to. I know how to do it if we had unlimited number of instructions. So there's for each possibility, we want to jump. For each jump, okay, so for each of the 4 configurations, it's either jump or not jump. So we basically want to say if it's in this configuration or this one, or this one, jump. How many instructions would that take up if we were to spell that out using only the commands we have available? I suppose... wonder if... So there's... So there's 4 possible configurations, okay? For each one, there's a B and a C value. So it may take 1 instruction to not one of them, 1 instruction to not the other. So let's say that's 2. And then we AND them. So that's 3 instructions. So that gets a 1 if it's that configuration. And then we have to OR it with our temporary variable. So that's 4. So 4 times 4 is 16. That's more than 15. That's just 1 more. And then we would need 1 more instruction. Oh, and the weight is also... The walk is also an instruction as well. So we need to... I think if we always jump or never jump, then we don't have to write out the truth table fully. We can just skip that and say just jump or not jump accordingly. All right, this is confusing. Let's just say jump configs. So this is the set of B's and C's for which we will jump. There's going to be a list, and there will be up to 4 because there's 4 different possibilities. But if the list is of size 4, that just means we're always jumping. So there's no point doing anything. We should just say jump. So script equals this. So if length of jump configs is 4, and script dot append how do we just say always jump? I mean, this could be the answer, just to always jump. That's probably not. Oh wait, we haven't accounted for the A and the D as well. Oh, this is so confusing. All right. Let's start by saying if A is a whole, then we jump, right? So how do we do that? In the fewest number of commands. I think that was basically what they already did. Let's have a look. So I reckon we always start with this, not a J. We always jump if A is a whole, okay? So that's we can never not have that line, right? So that's one line. Now, what was the other condition? If D is if D is a whole, we want to not jump. So whatever, so then okay, so we do not AJ, all right? And then we go through the configurations, and with each one, we OR it with J. So if J wasn't already false, we have a chance to make it true based on these configurations. Then after we've done all those, we have to deal with D. We have to say, okay, regardless of what J is at this point, if D is a whole, then whatever J was, just make it false. That's what we've got to say, right? So how do we do that? So afterwards, it would be script.append. So if D is a whole, so it's going to be it's just going to be this, isn't it? Yeah, this was already in the example. So we always start with that and we always end with that. Alright, I'm starting to get this now, but it's still pretty confusing. We always start with that, we always end with that. I think there's no arguing around that. We have to do that. So everything in between. Oh, we also need this. Walk. So is that one of the instructions we've used up? I don't think walk counts towards it, does it? It doesn't actually say. Does it? It can only remember at most 15 Spring script instructions. Is walk one of those? No, I don't think it is. All right. So we've only used up 2 out of 15, so we have 13 left. So for B's and C's, can we actually... But 13 instructions left, so there's 4 possible configurations for B and C. So we're saying if all of these configurations say jump, then we're just saying jump, full stop. How do we just say jump? Can we just set jump to true? Well, there's a hack we can do. We can just say this. Or a j. That says, because we already established that if a was false, j would be true. If a was true, j would be false at this point. So if we just do this, it will make it true. So this will just force it to be true. This is kind of, okay, whatever. Else. So if it's strictly less than 2 times 2 is 4. Yeah, okay, so if okay, so for each of the remaining each of the jump configs, of which there are at most 3, we want to add a bunch of lines saying to jump if B is that value and C is that value. Okay. So BC equals 4 BC in jump configs. So these are just going to be pairs, zeros and one, or trues and falses, whatever. So we're saying for this particular config, we're saying if B is this value and C is this value, then jump is true. So how are we doing this? We're saying how do we... Man, they've really limited our instructions here. Fine. So if B was... If we want B to be true, then we want... God. We don't have enough registers. We've only got one register we can use. J needs to be preserved. Am I thinking about this the right way? Is there something simpler that we could be doing? It could just be that you just meant to write it out manually in each case, because there's probably some easy script you can write for each configuration. I'm just trying to make one that covers all bases, but... Alright, so if B is false, we would do not B T. And then if C is false, we do... Okay, if you want B to be true, we want T... We just want to copy B to T. How do you do that? Basically, that's XOR. We don't have XOR. I guess you do this. You say script.append excuse me, not B T. So that's what we want if we wanted B to be false. And if we wanted B to be true, we should actually just say if B, we have to not it again. So $print not TT. Okay, that's a hack for basically copying whatever B is into T. Okay, that works. The problem is now T is fixed. Now how do we get the value of C in? Because we need one register spare to be able to do this, to be honest. Unless we say so now if we want T to be false, what's easier? Okay, so if we wanted C to be true, we would just do and if C. We would just and C with T, right? So if that means T will only stay true if C is also true. If we wanted C to be false, what would we do? What would we do? Not C. Yeah, but the problem is we don't have any variable to store the value of not C in, because we've only got one register and we're already storing something we need there. So I think the point of this, they're trying to get us to find hacky ways of copying values around when you've literally only got one register free to put stuff in. So I think it's just a so if we want so T is currently saying whether or not to jump. We want to do and that with the not value of C, basically. It's De Morgan's laws. So what we're trying to do is this. Not C and T. So if you use De Morgan's laws, which is an obscure thing that I haven't done since I was in school, that would transform to not C or not T. And now that second one, we can do using only one register, because then we just have to apply not to T, which will cancel out the previous not we did. Interesting. Or it's with C, and then not the result. But that would be 3 different things. That's too many. But the key is we would cancel that out. So it would actually cut out 2 instructions. How do we write this all? Hang on, I need to write this formula out on paper first. Maybe I'll see a simpler way of transforming this. So essentially, hang on. Let's just write out what we would want it to look like. So let's say we're doing that formula there. So we would do not TT. Then we would OR it with C. And put the result in T. And then we would do not TT. And then after all of that, we would T would now be basically the jump if B and C are these exact values. So now we would say OR this with T with J. So we do each of these for the 3 possible configs. So at most, as it's written, it would take up 1, 1, 1, 2, 3, 4, 5, 6. And that could happen 3 times. That's 18. That's way too many. But these, if we were to append this, so if this was here and this was here, they would cancel out. So we could actually just delete those 2 instructions. So that would actually end up being 4. 4 times 3 is 12. That would work. But if B was false, we wouldn't have this, so you couldn't cancel that out. So then you'd have 1, 2, 3, 4, 5. 5 times 3 is 15. But it's not going to... Alright, I think because some are over and some are under 13, I think it will actually just all even out. So I reckon what we can do is we can just say if we see 2 not TTs together, we can delete both of them. So if script, if the last instruction equals not TT, then just delete that. Otherwise, add the not TT. Okay, this is horrendous. All right, and then that might, hopefully it will work. And then we say else, and then we do the D in the walk thing. All right, I reckon that's the script. let's test it. So we want to... So let's say... See if it crashes horribly. If the robot crashes, that's fine, because that's working as intended. It just wasn't the right set of B's and C's. So that would be a good thing, at least. Define... Alright, let's just manually try a config. So this is going to be... Let's say 1001. Okay, those two possibilities. If B is 1 and C is 0, or B is 0 and C is 1. Those are the two places we jump. So then the script equals create script config. And then we've got to run the program, so we can say this for command in script, we do int code dot put string that command, and then it will auto put the new line character, and then it'll do the walk, which is also in the script, and then do the new line character. And then we do... So what did they say will happen? So if the robot falls into a hole, it will just give us an ASCII map. So we'll just see a bunch of weird characters. And if it succeeded, we'd get a big number. Alright, so just print... code dot get output. Just see what happens. Run it. 73. That's an ASCII. That's an ASCII character. What is 73? 73. Uppercase I. Hang on. Or let's just do this. While true, O equals code.get output. If O is none, break. Print O. So that should print out everything. It's printing a message. Let's convert it to ASCII then. Or can we just say result equals this, result dot append character O print dot join result. Alright, so it should just look like a sentence. Didn't make it across. Alright. So this is what happened. Oh, we've got a nice little map as well. So we went there, went there, there, went there, went there, there, and then we fell in. So we didn't jump at the A. Let's see what the script looks like. Not AJ, not BT, Or CT, not TT. Okay, it's a script that does something, I guess. So the only times we fiddle with J is when we put not A in. We do an OR. We do an OR. So at this point, the ORs can never make it false. They can only make it true, if it wasn't already true. And then we do an AND DJ. So we're saying if there is a hole, it's 4 spaces away, don't jump. So what happened was 1, 2, 3, 4. Ah, it's correct. It said don't jump because there was a hole 4 spaces away. That overrode the command to jump. So basically, because of this... Okay, it's working correctly. So because of this situation, we kind of can't wait. How do we get past this? We would say we want to jump if B is a hole. Okay, so let's try 0, 0, 0, 1. Let's just try that, I don't know. Wait, so we just have to try every possibility. So let's first just try empty list. Okay. Same obstacle, yeah, okay, so now let's try 0, 0. Okay. Let's try 0, 1. Okay. Let's try 1, 0. And 1, 1. So there, I've tried every configuration of just one jump. Requirement. Okay, now let's try every 2. Oh no, let's try let's try the 3. So it's gonna be 0, 0, 0, 1, 1, 0. So we're omitting 1, 1. Aha! We got a huge number. So let's say if O is bigger than, I don't know, 1,000, print O break. All right. If we got that number, that must be the answer. Like, there's no... You either get to the end or you don't. And if you get the end, then you get a big number. That's what they said. So that's got to be the right answer. Correct. So really, okay, I did a bit of manual work there, but really you just have to try every configuration of B's and C's. And I think because it's a bit weird, because if you look at this, it may seem like we're going over the limit for how many instructions we can have, but because of the weird way I've set this up, some go over the limit, some don't, but the ones that don't are under the limit enough that it all adds up to being at most 15 instructions, I think. I guess they chose that number specially. So it's really a case of... I don't... This needs a bit of manual work. I don't see a way of programmatically finding the right way to phrase these scripts. Like, okay, there's De Morgan's laws and stuff like that, which are not interesting, because nowadays we have computers to do Boolean logic, so we don't care as much about writing out complex Boolean expressions and simplifying them and stuff. I remember when I was in school, we had to do that. We had to use De Morgan's laws, we had to use the race hazard theorem for eliminating like sections of logic out of a long Boolean expression. It was such a redundant piece of knowledge and skill, because nowadays there's no reason to. Computers can handle millions of instructions. You don't really need to... It makes me wonder what GPT would do with this. Yeah, I think GPT would be able to come up with something, but I don't know if it would be able to keep it within the 15 instructions. Because that makes it quite obscure. Yeah. Oh man, I'm dreading part 2 now. That was hard enough for a part 1. A lot of people are going to stumble at this one. This is... I used some pretty... not advanced, but niche stuff there. Well, De Morgan's laws aren't strictly needed to solve this problem, but they helped. Well, let's have a look at... remind myself of what De Morgan's law actually is. Yeah, the general rule of thumb for De Morgan law is that if you have a Boolean expression and you invert everything, so every or turns to an and, every and turns to an or, every not turns... just cancel it out. Every lack of not becomes a not. So you basically invert every individual symbol, as well as every... It's hard to actually explain it in words. You basically invert everything. The result should equal the original one, but not quite. Well, yeah, sort of. Actually, the rule, De Morgan's laws, is literally just that. But it extends. So if you have a long piece of things, you can apply De Morgan's laws by treating this a minus b as a new symbol altogether. And then these are the generalized ones. Yeah, so once you sort of understand how the law applies, you can handle more complex statements. It's just... it's something you'd never really do nowadays, because just computers, you know, handle this stuff behind the scenes. It's just no reason to... I guess in electrical engineering, low-level electrical engineering, where you're just programming a thermostat or something, you may well still do this, because, you know, you're not actually writing a computer program, you're just putting a bunch of silicon chips together, and you do want to save on the number of chips you use, so yeah, use De Morgan's laws to cancel out some expressions, and that is actually what you would do. But anything more complex than that, and you just write a computer program and it just does it. It doesn't care how many expressions there are. But there was also another one called the race hazard theorem. I just want to see it in a simplified format. Okay, this is what they're saying. I don't even really understand the intuition behind the race hazard theorem, but it's another formula we had to use. Okay, that's A and B, or A, not A and C is equal to A and B, or not A and C, or B and C. I have absolutely no intuition for why that should be true, but that's a theorem we had to use as well when I was in school. Like, if you see a situation which looks like this, then you know you can eliminate the B and C. I guess... I don't even want to think about it. Okay. I guess we can look at part 2. I don't know if I'll do it now. Let's just get a sense for what we might end up doing. Part 2. There are many areas the spring droid can't reach. You flip through the manual and discover a way to increase its sensor range. Instead of ending your spring code program with walk, use run. Doing this will enable extended sensor mode, capable of sensing ground up to 9 tiles away. So now we've got E, F, G, H, and I. I don't understand. We've already found out how to get to the end. So why would this give us any different result? Like, surely the result we have right now would still work. They haven't changed the map, have they? So if we just ignore E, F, G, H, and I... Wait, let me remind myself what hull damage actually meant. Oh, are you damaging the hull every time you jump? Oh, so you're actually trying to reduce the number of jumps. Are we? No. We're not. It doesn't say anything about optimizing number of hull damage. Where does it mention hull damage? No, the hull damage was just caused by the asteroid. So they haven't changed the number of spring script instructions we can have. So if we just run it using run instead of walk, we can see E, F, G, and H, and I. But we can just ignore them. I don't understand this. Let's run it and see then. So, using the same config. So basically this translates to either not B or not C. Not B or not C. Okay. So if I say run instead of walk, and now we fall into a hole. But why? It's the same map, isn't it? same jump height. Is it not the same map? Oh, okay. So it says successfully survey the rest of the hull by ending your programming run. So I guess this is actually a different part of the ship. So it's actually a different map. Okay, I get it then. Oh my god. How can we... I had hard enough time translating B and C into at most 15 instructions. And now they want us to do it for B, C... E, F, G, H, I. D will still say the same because if there's a whole 4 spaces in front of us, we should not jump full stop. So it's now instead of 2 variables, we've got 2, 3, 4, 5, 6, 7. 2 to the power of 7 is 128. So I go from 4 possibles to 128. How can you possibly fit that in 15 instructions? Oh, this is just more messy De Morgan stuff, isn't it? Is there a better way of doing this? Maybe we just want to... actually, so when we fall into a hole, it gives us a map. So do we actually want to build a map of what the hole looks like? Thing is, we don't know where in the hull we saw this. So that's not helpful. Like, the only way we can force it to fall into a hole is by, you know, letting it just walk into a hole. But you can't tell it when to do that. So we can't just draw a complete map of the hole. I think... So if we look at this situation here... So if we're using the same method as before... We definitely jump here, we land here, jump here, land here, jump here, land there. So why doesn't our method... because we were jumping early. So here, the only way to get across is to jump here. Because there's a 3-space gap. So whenever we see a 3-space gap, we know what to do. It's just how do we encode that into a bunch of oars and hands? That's really, really confusing. Alright, DJ. See you next time. In fact, I mean, I'm probably not going to do this part 2 now. I'll probably leave it till tomorrow. Another time. It's a good thing for me to think about. Yeah. Yeah, I think I'll just stop the stream now. Leave this till next time. I don't just want a stream where I'm just scribbling stuff for hours. Yeah, so I guess I'll stop there. It's definitely an interesting problem, but it's also quite specialized, unless there's a clever way of solving this without needing specialized logic knowledge. I'll think about it. Maybe I'll come up with something. All right. We've got this Boolean expression thing. Seems quite tricky. We solved it for B and C. So, okay, so A and D. Okay, you've got, okay, originally we had A, B, C, and D. If A was a hole, we would always jump, for sure. Otherwise, you would fall into the hole. So we need so A doesn't matter. Okay. Similarly, D, if D is not a hole, well, if D is a hole, we never jump, because we would land in a hole. So D doesn't matter either, or at least it's a trivial check. So we figured out what to do with those two. Alright, and then it came down to B and C. And we found a Boolean expression. So I think the general case, it would not be possible to write a script in only 15 instructions that could solve this with E, F, G, H, I added in, because there's just too many possibilities to account for. So I reckon it's actually going to be much simpler. Just the expression we need is going to be simpler and could be probably even be checked, derived by hand. We just need to find some cases where it fails, analyze those cases, reassess. Alright, before I do that though, there's something I wanted to check as well. So, let me test this out. Okay, it's screwed up. Oh, there we go. Alright, this is just a little Java applet I downloaded. It's a truth table solver. You give it a truth table and it gives you a Boolean expression, a simplified Boolean expression as a conjunction of thingies. So let's try doing this. So we've got A, B, rename these properly, C and D. All right. Now, so, oh, my coffee's ready. Hello, dear Jay. Just had to get my coffee. So, I'm testing this applet out for part 1. So the idea is if I give it an assignment of zeros and ones that would result in a jump for what I want, then this program would use what's known as the, I don't know, the McKinsey something or other algorithm to find a simple Boolean expression which would describe what I'm trying to see. What I'm trying to get. And we've already solved part 1, but let's see what it gives us, and then we can try it for part 2. So we've got A, B, C, and D. Now we know that for A... Hang on. Let me open this up. So jump is 1. 0 means don't jump. Okay. So hole... If it's a ground, it was 1, was it? Let me check what it actually was. Yeah, if it's ground, it's 1. If it's a hole, it's 0. All right. So so if it's a hole, we jump. So we just do this, right? If A is 0, there's a hole, we jump. Okay. Now for the D's, if D is a hole, we don't jump. So for all the zeros, well, this one is what's D? Does that mean we're hoping that situation doesn't come up because it's impossible then? So for all of these, we'll change them to, if it's 1, we'll change it to D, I guess. Oops, I got disconnected. Okay, I'm back. I got disconnected briefly. So I got disconnected again. What's going on? It looks like the connection's a bit temperamental right now. So it's got to be an easier way to enter this. Does D mean don't know? Alright, put D for everything we don't currently know. Just put D's for all these. Alright, now, if the letter D is... So if the D variable is 0, that means it's a hole, that means we don't want to jump. So that's 0, that's 0, that's 0, and that's 0. Okay. So, okay, we can just change. I don't know. Okay. So, try solving that for now. It gives us A dash. Okay, good. That's about right. We jump if there's a hole in A and don't care about anything else. All right. That's a starter program. So when we find an example where this fails, we would have to adjust for B and C. So for example, we found a case where we needed to jump. Which was well, let's try using this process to solve the problems. Let me change back to this. So let's take this out. Or config is just an empty config. So this should be equivalent to just doing not a j. So if we run it, but we need to walk, not run. Okay, so it fails. So we see this. We're walking, we're walking, we're walking, and then we jump. No, we fall. It's because of the D. All right, so that's fine. So what should we have done? We absolutely should have jumped from here, where B was 0 and C was 0. So what we're saying if B is 0 and C is 0, we must jump. No. What? No, that's not what we're saying. We're saying A, B, C, D. We're saying B and C are both holes. Should we always jump? That's the only way to handle this particular case. So yeah, let's say if B and C are 0, we jump. So we're adding that case in. So can I make this a bit bigger? It doesn't exactly zoom in. Hang on. I can't resize it because of the stupid taskbar. Hang on. Oh, there we go. Let me just resize it in OBS then. Okay. Alright, so we're saying if B and C is 0, then we jump. So for this one, jump. So we change all the D's to 1s, if it's the case we're looking for. Okay, now solve it. So we're saying A plus... No, that's not what we're trying to say. What are we trying to say? We're saying if B and C are 0, we jump. But not if D is 0. This doesn't seem right, is it? A plus D, A dash plus D. Oh, I'm getting mixed up with all these letters. Should we start afresh? So we say we don't jump at all, okay? And every time we find places we jump, we change. This. Alright, so well, we can take A and D out altogether because we know how to deal with them. They're independent. If A, yeah, we just combining A dash and D with whatever else we have. So it's easier if we just take A and D out. So B, C. Okay. So what have we said? We've said if B and C are both 0, then we jump. So now we've got B dash dot C dash. Okay. So let's try that. So we go back to our script. And we put okay, take this out. It's a bit confusing. Run that. Okay. So we're saying if B, so we're doing B, we're adding in B dash, not B, and not C. So how do we do that in terms of expressions? It's going to be not B and not C. Not B and not C is the same as not B or C. Using De Morgan law. I need to scribble some things down. This is too confusing. And say not B and not C. But how do we describe that if we only have one temporary variable? We can't. So it's got to be a sequence of. So it could be not B or C, but how do we do B or C? So right now T is empty, right? We have not used T. So we can do just B or T, or B, T. And then we could do or C, T. So that isn't, T is now holding B or C. And then we do not, all of that. Not TT. Okay, so this should now be equivalent to what the truth table is telling us. Let's try running that. And then we fail, as expected. So we find another case where it doesn't work. So let's try it. Have a look. So we've got this situation. So here we had B and C are holes. We didn't jump. Ah, because we didn't put the T in the J. Hang on. We put it in T. And now we need to OR T with J. Okay, try that. Okay, so now it fails. What's the situation now? So we've got this. So we've got a hole in front of us, but we didn't jump. So we needed to jump earlier. Where did we need to jump? Here? We could jump here, or we could have jumped here, actually. It doesn't actually matter. Not here. So that's A, B, C, D. So definitely not there. So what is the... How do we describe this? Well, there's not a unique answer here. There's two places we could jump, so does it matter which one we do? So should we say if B is ground and C is hole, we jump? B is ground, C is hole. Okay, we'll try that. So B is 1, C is 0. We'll jump there as well. Okay. Now it's just not C. Okay. Should we somehow I don't think that's good enough. Alright, well we can try this. So we say so just take this out. This process is not... Is it effective? I can't tell. So we not C and T, and then we OR T and J. Alright, so now we're just doing not C. Oh, that works! So we just found a simpler... Oh yeah, but that is actually what we were doing, isn't it? Not C, because B was independent, because both 0, 0 and 1, 0 are jumps. No. Oh, it's just a different solution to what we found before. But this works. Okay, so not C was a solution to part 1. And it gives us 193 whatever. And that's correct, I assume. Yeah, because if you got a number at all, it's got to be right. So, this process gave us a Boolean expression. It's a manual process. So what if we try and do this for B, C, D, E? Okay, so this is where it gets hard now. I don't like this configs thing. We'll just cut that out now. In fact, just take that out. I don't think we'll be reusing that. Let's take it out. So this is the program for part 1. Okay. So now, try for part 2. Just for fun, see what happens. And of course it fails. Alright, so... let's take out everything. Just go back to the A and D. Just the most basic. Okay. So this fails. So where would we need to jump here? We have to jump here. It's not possible anywhere else. Also, how many letters do we have again? It's... Oh my god, so many. B, C... Well, D we know doesn't matter. So it's B, C, E, F, G, H, I. Oh, but that's too many to put into the truth table. B, C, E, F, G, H, I. That's 127. Okay, that's not too bad. B, C, E, F, G, H, I. B, C, E, F, G, H, I. So let's analyze this situation we've got. We've got... When do we want to jump here? It's got to be here. So if A is irrelevant, B is a whole, C is a whole, D, well, D is irrelevant because we know about that. So it's B is a whole, C is a whole, and E is a whole. If you ever have B, C, E all being wholes, you gotta jump. Because otherwise, if you go forward 1, you would now have... A would be a hole, and you have to jump, but you would land in the hole at E. Yeah, okay, so B, C, E being 0 means we must jump. B, C, E. Okay. So it's not B, not C, not E. So right now, that's what we've got. So let's try that. So how do we do this? Not B, not C, not E. So if we De Morgan that, we get not B or C or E. Okay, yeah, we can do that. So as before, so it's going to be so first we do put or B. Okay, let's leave some gaps here. Or okay, we do B, and then we OR that with C, and we OR that with E, and then we knot the whole thing. It's going to be not TT, and then we disjunct, whatever, I don't know the terms. Combine that with our current T, which is like the A. Okay, so that's 1, 2, 3, 4, 5, 6, 7. Okay, that's fine. Run it. Alright, got a different fail. So here, we didn't... Okay. So if B... So here we have to jump, because otherwise we have this situation. It's not the B's and C's and E's that are the problem. It's the hang on. So it's A, B. Oh, sorry, I've got the truth table up. Kythius, welcome in. Oh, I'm doing a kind of a nasty problem involving Boolean logic. This is kind of specialized. I'm surprised this is, unless I'm doing this in a really obscure way to solve the problem. Maybe there's a better way, but this is kind of using some pretty obscure stuff to solve it. All right, so basically we're trying to give a script to a guy who jumps over holes. But the catch is there's a very limited set of instructions we can give him. We can only give him at most 15 instructions. So based on what he sees in front of him, he has to know whether to jump or not. His jump can take him forward 4 spaces. So if we ever see the situation where, okay, so A is in front of us, that's ground. B is a hole. C and D are irrelevant. E is a hole. So if B is a hole and E is a hole, we should jump. Hang on. So whatever I did before was too restrictive. It's not about C. It's actually just B and E. If B and E are both holes, we jump. So okay, so it's this section here. B and E. Okay. So it's not about C. C is irrelevant. Okay, okay, fine. Change that then. So take out C altogether. I don't know if there's a way to programmatically do this. I'm just doing this manually, but programmatically would mean you have to keep trying expressions, seeing what the result is, and changing them. So take out C. Just delete it altogether. So we're saying if... Yeah, okay. If B and E are holes, jump. Alright. So now what? So in this situation, B, C, D, E. Now this is a B and E are holes. However, F was also a hole. That's a problem. So you have to go one place up. I think we need to jump here. So what is the... Basically it's if C is a hole and F is a hole. So it's A, B, B, C is a hole, F is a hole. That means we won't be able to jump before that first hole because we'll land in a hole. So if that situation comes up, then we need to jump. If C is a... Can you jump continuously or only once? Well, you're giving them the script, so every time, every turn, it's automatically going to look at this script, depending on what it sees in front of it, and follow it. So it's got to be the same script for every situation. You can jump. If you jump, you land 4 spaces forward, and then it reevaluates based on what it's seeing from there. So it's just always evaluating this. So he will jump multiple times throughout this. I don't know how long this terrain is. So in this case, it seems So if C is a hole and F is a hole, C, D, E, F, then clearly we can't jump at B. So we either jump now. Wait, no. C, D, E. So we should have jumped here. No, not here, because 1, 2, 3, 4, we would have landed in a hole. Yeah, okay, so C is a hole, D, E is a hole, and F is a hole. Then we're forced to jump now, because if we wait till next turn, and jump, we'll land in the E. So we're saying if C is 0, F is 0, and E is 0, we jump. Okay, try and code this in. C, F, E. C, F, E. C, E, F. Jump, 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 jump. So there are more here. So now it's more complicated. B, Okay. Well, we have enough expressions to be able to do this. So C, not E, not F. All right. So for each clause, we can actually just copy paste this. So this new clause will look like damn it, how do we clear T? We want T to be false now. They're really limited what we can use. We can't even use the values 1 and 0. We have to create them out of these variables. So T is now holding garbage. We want to, okay, so we could do T with not T, T or not T or, no, wait. If we got this far, if A was a whole, we would already be jumping. So otherwise A would be 1. So we can do not A T. That would clear T, assuming A is, yeah. You have to come up with all these hacky ways of storing data. Okay, so that clears T. And now we do or C T or E T and or F T. Not it, and then or it with J. Okay, try running that. All right, another failure. Right, so how many expressions have we used now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we can only use 3 more. Alright, let's see. Landed in a hole. Because we jumped at the last second, and that doesn't work. Alright, so where should we jump? Ooh, I see. So we should have jumped 1 space before. So here. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then we would have been fine. Okay. What is the situation that describes this? It's if B is a whole, C is a whole, D, E, F is a whole, G, wait, but we can only go as high as G, H, I. Oh, we can, okay. B, C, F, and I is a whole. If B, C, F, and I are wholes, then we jump. This is gonna take too many. Alright, let's try that. So B, C, F, and I. Now it's hard to okay, so B, C, F, and I jump there. Jump there. Jump there. Yeah, jump there. And now F becomes 1. F goes back to 0 here. But C is 1. C goes back to 0 here, but now B is 1 for the rest of it. Okay, so that seems to be... Oh, for goodness sake, what are we supposed to do with this now? I think the problem is we're asserting lots of zeros here when we don't actually need them. I think the problem is all these places where I have 0, I've left them by default. It should actually be question mark. And we should be putting the 0s and the 1s in as we find them. So the 0s should all be question marks. And when we find a place we absolutely must not jump, we then put 0. Because right now it's asserting that we have to not jump at these places, which is not quite right. So if I just try B, C, F, I, and C, E, F. What do we already have coded in? Here it's B, E, and C, E, F. So instead of this one, we could do B, C, F, I. Let's try that. B, C, F, I. Oh, this is a simple one. Oh, yeah, but that's the one we cut out. We don't have enough expressions for this. Oh, man. How many expressions have we used now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We'll have one more expression. So we've got CEF. We took out the BE. So what if we just put BE? No, not. Yeah, B-E. What's up with this one? I think we've got to go start again, but we've got to get rid of the zeros. Because that's what's messing this up. So, all the places I've left 0. Okay, so all the places I've placed 1, we were absolutely sure that for that sequence we needed to jump. So, everything else we can put D. I assume this just means we don't have a preference for these ones. Now to start with, it's just going to give us something dumb like always 1, because that would technically solve this, but then piece by piece we can add in the zeros we need. Can we... Oh, we can do... We can't do them together. There's got to be a better tool for doing this. Like, I would want to say... We don't actually want to work with truth tables here. We want to actually insert in expressions and simplify said expressions. Maybe there's a better tool for doing this. So right now, if I solve it, 1, okay. So as we find cases where we need to not jump, well, we can add them in as well. So let's try this then. Or let's leave in the B, C, F, I for now. Take this out. B, C, F, I. Okay, so we found a situation where... So we should have jumped here. A, B, C, D. So no. This is not 1, this is 0. We need, how do we do this? Take this out. Okay, just never jump for now. This is what happens if we never jump. Okay. So we need to say... If... B... So here, if... B is 0... Hang on. Let's just do what the truth table is telling us. The truth table is telling us, couldn't you just jump as long as d equals 1 and otherwise walk forward? That's currently what we're doing, actually. If I take out all this stuff, this last expression here says, if so right now we're saying if A, which is right in front of us, is a whole, jump. Because that's bona fide, we have to do that. And then at the end, we're saying if D is a whole, don't jump. So we can add in jump. We can just make it jump always, because that's actually what the truth table is telling us right now. But it's going to come up with a situation where it fails, probably, and then we'll have to adjust. So let's say, so to tell it to always jump, I guess we want, so if A is a whole, J will be 1 already. If A is not a whole, then A will be 1. So we can just do A or J. So now J will be 1, and will specifically not jump if D is a whole. Yeah, so we always jump unless D is a whole. That's what it's now doing. So we can try running it. And then, and that matches the truth table right now. Okay, so then we come up with this situation where we jumped like here. We ended up here. And we can't jump here, B, C, D, E. So this situation, B, C, D, E, F, G, H, I. So the problem here was, so we land A, B, C, D. We land at D. E was a whole. So that forces us to jump again. And H was a whole, and that kills us. So if E is a whole and H is a whole, we absolutely must not jump. We found one situation that we can code in where we mustn't jump. E is a whole and H is a whole. That's quite simple, simply expressed. Okay, let's put that in. So if E is a whole and H is a whole. Wait, what? No, I don't think I've got A, B, C, D, E, F, G, H. So if I jump A, B, C, D, I land here. And then E being a whole forces us to jump. Why did we have this jump then? That's killing us. Well, that was wrong. Where did I get that from? I don't even have that written down. Might have to reset the whole truth table. Alright, so E and H are 0, we must not jump. In this truth table might be overkill. If there are only like 2 or 3 absolutely firm statements like we've just found, EH0 means we must not jump, and that's really all we need to do. I just thought it might be more complicated than that. But it looks like there might actually be just a simple way of describing this situation which doesn't need a truth table, so I don't know. I can't really imagine he was expecting us to do what I'm doing right now. Don't jump there. I think I've made a mess of this. I need to start the truth table from scratch. H or E? Okay. Do what the truth table says. H or E. So, instead of this, instead of always jumping, we're now going to say oops, E, H, and then just put that in. E or H. If E is one, or if E is ground or H is ground, jump. Alright. Now what? So now we've jumped. We've landed here. And then we were forced to jump again and then land in a hole. But we can't see that far ahead. A, B, C, D, E, F, G, H, I. We can't see that far ahead. I hate this. C, E, F, G, H, I. Maybe we don't need this many terms. Let's think. Are there any of these that we just are irrelevant, that we don't need to look at all? Clearly we need E and H. So, do we need anything else? Can we eliminate anything else? Never had G come up. We tried something a bit simpler. Let's remove most of these terms. Okay. Go back to just having E and H. That's what we've got right now. Okay. So we said if E and H are both 0, we mustn't jump. And in any other case, we can jump. Alright. Whoa, we don't know. We just know that we mustn't jump for E and H. So then, when this is what this is currently doing. And if we run it, we get this situation. So what is the key flaw here? We're jumping. We're landing at a spot in front of a hole, which forces us to jump again. I reckon if E is a hole, we just shouldn't jump. Because that means we're landing at a place which forces us to jump, and that means there's always a situation where someone could have placed a sequence that forces us into a hole. So I reckon if E is ever 0, we just shouldn't jump. So let's just do that. Let's say if E is 0, we don't jump. Alright, so that's... if E is 0... Okay, so the truth table is now saying just don't jump, full stop. Fine. Because we don't have any other data to go on. So I'll just disconnect again. Disconnected again. Alright. God. Okay, just follow this process again. This time we've only got 2 variables, and every time we find we need a new one, we can add one in. So, let's go back to not jumping. Just rely on A and D alone. Alright, so take this out. This out. Okay, run. So, let's see. What happens? We don't jump. We can't jump here because... Yeah, of course. Alright, so A is a hole, B, C, D is a hole, we're screwed. So if we get here and we see B is a hole and E is a hole, I mean, we addressed this before. So clearly B is actually needed as well as E and H. So we'll add in B. Let's try and put them in order. So let's say B, E, H. So we're saying if so what are we saying? If B is a hole and E is a hole, we must jump. So B, E is 0, we must jump. So B B, E, B, E, and put these to D for now. And the other situation is if it's E and H are 0, we mustn't jump. But that conflicts with BE. I think that's unresolvable. I think if we ever had a situation where B, E, and H are all wholes, you're screwed, are you? Is that what this is saying? Let me draw this out. So B is a whole. E is a whole. H is a whole. Yeah, you are screwed. Alright, so in that case, just leave this as D. It can do whatever it wants with that, because we just have to pray that never comes up. It won't, because otherwise it's an unsolvable. Well, it's solvable by jumping earlier. So if you see... So basically, BEH 0 means you've lost. So if you go one space back, then CFI means you have to jump. But do we really want to code that in? I'll make a note of that, but otherwise you end up with B, C, whatever. Okay, so just leave that out for now. So we're saying EH is 0, we must jump. Oh, mustn't jump. And BE is 0, we jump. Okay, try that. E and not B. Alright. E will not be. How are we going to code this? Not be. Okay. So we OR that with J. And then we do not be. Store that in T. And then OR that with J. So E or not be. What the? This is a simple one. Oh, why did this fail? So here, so if B is a whole and E is a whole,
we must jump. Well, that's what we said. Why isn't it doing it? Is this correct? E or not B? I don't think I've even put it in correctly. If E and B are 0, we jump. But we had this one up here. But that's impossible. We can't deal with that. So B and E 0 jump. B. These shouldn't have been 1s. My god, I'm mixing these up so much. It's just not B. Oh, this is just endless. It's gonna keep going around in circles. All right, fine. Just try that. There's got to be a better way to solve this problem. So it's not B. Still failing this one. We're saying jump if B is a hole. So why didn't you jump? Because there was a hole. A, B, C, D. So what should we have done here? B, A, B, C, D. I see. We should have actually jumped even earlier. So it's B, A, B, C is a hole. So if C is a hole, E is a hole, and F is a hole, then we must jump. See, now we have to throw in more variables. Ugh. Maybe truth tables is not the way to go. Maybe we just write out all the possible situations and somehow try to find out a way of... So, what have we learned? That E is 0, H is 0, then we absolutely must not jump. Okay. If B is 0 and E is 0, we absolutely must jump. If C is 0 and F is 0 and E is 0, which is this situation here, we absolutely must jump. Because there's no other chance we'll get. What else? Okay. I don't know how to solve this. There's got to be a better way. It's such a tight restriction. 15 expressions to describe the script. I mean, okay. I've got 3 expressions now. I can try and do those 3. E, H. So let's see. So we're saying if B and E are 0, we jump. Okay, I don't know, just do that for now. So it's not B and then no. Okay, so it's or B T or E T. And then we want to do not it. And then or it with J. Okay, so that handles the B and E being 0, we jump. But that's like 4 expressions used up already. Now, we want to deal with C, F, and E being 0, we jump. Okay. C, F, and E. So we have to clear the memory of T, I guess. By doing... So A is assumed to be a hole right now. Not a hole. No. If it was a hole, we'd already be jumping. So it's not a hole. So A is 1. So not A and T to clear T. And now we want to do CFE. So we want this process again. But it's going to be CF E. And not. And then add that to J. And then I'm guessing this is the CFI situation, is it? But now we've used up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. We can add 3 more. We can't fit any more in. What? This is so ridiculous. Unless they said that we don't have that restriction anymore. No, they didn't say anything about that, so it's same restriction. Up to 9 tiles away, this data is available in 5 new read-only registers. All other functions remain the same. Right. I don't know. I'm completely clueless about this one. I know what you would do to solve it. It's just this restriction, it makes it too much of a puzzle. Which I'm sure I could solve if I wrote out all the possible situations using the truth table solver, but is that really expected? Like, okay, there's probably a way to hack in, like, certain pieces of logic, even with the small amount of possibilities we have for inserting instructions. I don't think the truth table solver is even going to help us. Probably don't want to use that anymore. Well, I don't know. Okay, let's look at this situation that we've got in front of us then. What is this? So how do we get past this? We can't wait till the end. We can't go 1, 2, 3, 4, 1, 2, 3, 4. Wait, we can go 1 space from the end. So why are we jumping? We weren't jumping here. Why not? Why not? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2. Oh, because we didn't tell it to. So we see, if we wait till the end, we go jump, 1, 2, we land there, and then we jump, we land there in the hole. So basically, A, B, C, D, E, F, G, H, I. It's C. So it's C is 0. We already had this before. F is 0. And I is 0. Why did I do C, F, E? Oh. Well, that is also a situation. First of all, let's put these in order. So let's try C, F, I then. I just want to see what happens. C, F, I. So CFI is also a fail. We need to jump there. But we can combine those two. We can say if C, so it's not C and not F, and then it will be either not E or not I. So that's the same as E and I knotted. We shouldn't be needing to do this much algebra. And then that whole thing is not C or F or E and I. Interesting. Let's try this. So we could probably fit this one in because we've done... So we do not... Okay, so we clear A. Clear T, even. We do E and I. So it's going to be E. And then and I. And then the result, we want to do or F. Or C even. And or F. Not that. Okay, so now we've managed to squeeze in an extra expression because it had C and F in common. How often are we going to be able to do that? Okay, now what? We jumped there. Alright, so where should we jump here? So there's 2 spaces here, so that would mean we would... We need to jump from this one, so we need to land on that one. That means we need to jump from this one. That means we need to jump 1 space before, but... We need to jump from here. Well, what's the... A, B, C, D, E, F, G, H, I. This will just go on forever. They'll keep on having... keep on coming up with? There's 128 possibilities here, so every time I rule one out, it'll just come up with more. What other approaches could we do? Could we just randomize? No. I mean, this situation right here, can we actually, we can't predict it because we can't see what that, we can see A, B, C, D, E, F, G, H, I, but J matters. If J was a hash, we would be okay because then we could go from here. Oh, I don't know. I think I'm gonna stop here. This might be one way I need to look up a hint just to see if there's a particular avenue I should be going down, because this Boolean algebra is ridiculous, and there's no way we would expect to be able to do this Boolean algebra. Like, you don't do this. Who does this anymore? It's like we have computers now. I even studied electronics, and we did do some of this. De Morgan's laws and stuff, but definitely not restricted to only 15 expressions. We have entire breadboards. We can put as many logic circuits as we need. There's probably some easier process that I'm missing. Alright, I'll leave it here and I'll look up some hints and then try a different approach next time, because it's just... Well, the truth table program is pretty cool, but I don't think we would be expected to use this. Speaking of solvers, though, what about Pi Z3? Could that be of use? Well, it's not quite... I don't know. Alright, I'll just stop here. Am I even online right now? OBS is showing me a cross symbol now. What's happened? I think it might have disconnected. I'm still recording at least. Alright. Yeah. I'll have another long think about this offline. So... Okay, I am back, and I have solved part 2, but I kind of looked up the answer. And, I mean, I was originally just looking for hints. So I looked at the, you know, the Reddit page where people posted their solutions. I just wanted to see some hints, and it seemed like there isn't really a good way to solve this problem. Everyone, at least all the solutions I read, people were literally just trying by hand the same process that I followed, and eventually they just stumbled upon something that works. So as far as I can tell, there's no elegant way to solve this, and for that reason I wasn't interested in continuing with the process I was following. I literally just copied in the program that someone else pasted, and it worked. So it wasn't really a programming problem. Let me show you what I actually... Oh. Here it is. This is just one possible program I copied. And I mean, they're not universal. Sometimes they might not work for some people's inputs, but this one works for mine, and it worked for the other guys apparently. So yeah, it wasn't a programming problem in my view. I didn't actually like this problem. Some people liked it. That's cool. They saw it as more of a logic puzzle using pen and paper, but that's not really what I'm using this site for. So yeah, it was an original problem, at least. I can say that, but not my cup of tea. Okay, one person did actually solve it programmatically, and they said they used Z3, and I was thinking about that, and you could probably use Z3 to solve this. It wasn't easy to do though. They had to be really clever about the way they input the constraints and everything. So it was more work than really just fiddling around with test cases until you find something which works. So as far as I can tell, it's not really a programming problem. It's just this. Okay, so yeah, this is, come to think of it, this is the only Advent of Code problem I've ever given up on. But it's not because it was too hard. I reckon if I just continued with the previous process, I would have got there eventually. It's just, I don't think I would get anything out of it, so I didn't. Alright, so I was just making this video now to round this off, because the last 2 or 3 hours I didn't really yield anything. Okay, so that's that solved. And next time I'll be back with... Let's have a look at the leaderboard. Well, I mean, surprisingly, a lot of people did actually solve it, so I guess they just kind of... It's believable that people did it quickly. I mean... Oop, hang on, I haven't got the page open. Because... Like, I saw some posts... saying... that they got it really quickly. They just tried something and it happened to work. So it's kind of a luck kind of thing. And so for that reason, you'd expect a lot of people actually solve it quite quickly. But... So how many... Oh, I keep forgetting how to... Yeah, stats. 21. Well, it's the same as all these days. I guess there's not much... You can't separate much here. Okay. So... First ever failed problem on Advent of Code. I have read that apparently 2019, the year we're doing, was considered peak difficulty. Either this or 2020, or both. And I guess this was one of those problems that was really specialized. Yeah, because people were talking about using De Morgan's laws and all these complex logic stuff. You know, the stuff that I did back in school, but it's not. You never need to do it in the real world. So yeah. I was saying... I think if you removed the 15 instruction restriction, or just made it bigger, it would become a programming problem, and I think I would like it more, even if it was easier. Because then you would actually have to work out the truth table, and every time you find a test case, you'd be able to fill in more rows of your truth table. And this can be done programmatically. And then you would eventually, given a truth table, you can actually concoct a formula, and you can apply De Morgan and stuff to simplify that as a set of conjunction of disjunctions or disjunction of conjunctions or whatever. So 15 instruction limit was a bit tight. If it was just a bit bigger, I think it would have been a good problem. And one that actually tested your skills instead of your ability to just... your patience. Let's put it that way. Not a patience tester, but a programming skill tester. Okay, enough rambling. Let's just take a sneak peek at 22. It's a card game.
Card shuffling. Okay. Maybe rotating arrays or something. Looks interesting. Okay, next time. See you. Bye-bye.